Hi there. Which of the following functions have a graph that does not have a vertical asymptote? Ooh, this is a nice question. The way that you can tell is if you can figure out which denominators could never be zero no matter what. Or in other words, which denominators show that we don't have any restrictions on x. This one could never be zero because you've got x squared, which means that you'll always have a positive and then a positive on top of that. So there's never going to be a zero here. You're just going to have a more positive positive. Right? So that one will not have a vertical asymptote. And if you couldn't tell just by what I said, you could take that denominator and set it equal to 0 and solve for x. Take the square root of both sides, and then you would get that x would have to be a non-real number to get that denominator to be 0, and we're only concerned with real numbers that would create a 0 in the denominator because we're dealing with graphing on the xy plane, and on the xy plane you don't see complex non-real imaginary numbers. So that's how we know A could never have a vertical asymptote. And this one can definitely have a vertical asymptote because if we let x be the square root of 3 and you plug that in to x, or into the function, f of the square root of 3 would be 1 over the square root of 3 quantity squared, which simplifies to 1 over 3 minus 3, which is undefined. So that means you have a vertical asymptote at x equals the square root of 3. So can't choose B there. What about the next one? Oh yeah, that could definitely have a vertical asymptote at x equals 7. And this one as well at x equals 0. So the only one that can't is that one. Determine the equations of the asymptotes for the graph of the rational function. So now that we're looking at a given image, determine the equations of the asymptotes. Okay, well that's easy because they're straight vertical and horizontal lines. So I don't have to figure out like a slope and an intercept and all that. For the vertical asymptote, this one right here, it's going through the x value 1, 2, 3, 4. So everywhere we go on this vertical line, every single point on that vertical line would have an x coordinate of 4. Your y values would change, but your x value would stay the same all the time. In other words, your x value is a constant. So you would have a vertical asymptote at x equals 4. Now the y values will stay the same through the horizontal line, and it looks like that's going through y equals 1. So that would be my horizontal asymptote at y equals 1. Number 16, identify the horizontal or vertical asymptotes in the graph and state the domain of f. All right, so our horizontal one here goes through y equals -2, and the vertical asymptotes go through x equals 3 and x equals -3. Okay, so that's vertical asymptote, horizontal asymptote. And then what's the domain? Well, the domain is what x values can be, or restrictions on x. So the domain based on the vertical asymptotes is x values from -∞ to -3, -3, to 3, and 3 to infinity. So those are the intervals in between the asymptotes. So we have the correct choice would be here for the asymptotes, and the domain here. Number 17, determine the equations of the asymptotes for the graph of the rational function. Oh, these asymptotes are oblique. They're slanted. So this time we're going to do the y equals mx plus b thing. So first of all, let's look at, oh wait, this one's not slanted, I guess. This one looks, sorry, it's hard to draw on this thing in a straight way. There's no traction on the screen. All right, so there's my vertical. That's actually a vertical asymptote, and that's going through the x value 2, looks like. But the other asymptote is oblique. I meant to change color there. Okay, so we're looking at this slanted line, which has, looks like the y-intercept is 0, and the slope up 1 over 1, up 1 over 1, looks like a -1. So I'm going to say that the oblique asymptote is at -x plus 0, and we don't write the 0. And then we have a vertical asymptote at x equals 2. How we doing on time? Yeah, we'll stop it right there.